If you scaled the peacock mantis shrimp up to the size of an average human, its punch would hit with the energy of a small car colliding at highway speed. That is not an exaggeration from a clickbait article. That is the math from peer-reviewed research at Duke University. The strike is so fast that water cannot get out of the way fast enough, so it briefly turns into a vapor pocket. And when that pocket collapses, it releases a flash of light, a snap of sound, and a burst of heat that climbs to roughly 5,000 Kelvin. All of this happens in a creature you could hold in one hand. But this story doesn't start with that punch. It starts with what a peacock mantis shrimp actually is, because once you understand the body, the rest of what you're about to hear stops sounding like a cartoon and starts sounding like one of the most absurdly engineered animals in the ocean. A peacock mantis shrimp is a crustacean, not a shrimp in any meaningful sense, and not a mantis either. It is roughly the length of a banana. It lives in burrows in shallow tropical reefs around the Indian and Pacific Oceans, mostly in places like Australia and the Philippines. Its shell is painted in greens, reds, blues, and oranges that look airbrushed. The eyes ride on stalks and swivel independently like two small periscopes. And tucked under the front of its body are two folded clubs that, when triggered, become the fastest mechanical weapon in the animal kingdom. The reason that weapon is even possible has nothing to do with muscle. A muscle cannot move that quickly. According to research from the Paytech lab at Duke University, the mantis shrimp's striking arm uses a saddle-shaped piece of its own exoskeleton as a spring. Picture a tiny crossbow built into the animal's elbow. Slow muscle slowly bends the spring, a small latch holds it cocked, and when the latch lets go, every bit of stored energy releases at once. The club doesn't push. It snaps. How fast does it snap? In the same research, the club accelerates at around 10,000 G. That is the kind of acceleration you would expect from a small caliber rifle bullet, not from a piece of an animal. Peak strike speed is in the range of 12 to 23 meters per second, and the entire strike is over in under 100 microseconds. That is less than 1,000th of a second. By the time you finish blinking, the mantis shrimp could have completed dozens of full punches. The water itself starts to matter at those speeds. When something moves through water that quickly, the pressure on the front of the object spikes and the pressure on the back drops to almost nothing. According to the Nature paper by Patek, Korf, and Caldwell, published in 2004, that low-pressure pocket on the backside of the club causes the surrounding seawater to flash from a liquid into a vapor bubble. Scientists call this cavitation. The mantis shrimp is moving its club so violently that the ocean cannot keep up. It briefly punches a hole in the water. A few microseconds later, that vapor bubble collapses. And the collapse is the part that stops sounding biological at all. When a cavitation bubble implodes, the surrounding water rushes back in from every direction at once. The pressure at the center of the collapse becomes extreme. Inside that tiny point, temperatures have been measured at roughly 5,000 Kelvin, which is comparable to the surface of the sun, and the implosion releases a faint flash of visible light and a sharp snap of sound. That is a real phenomenon, documented in the same Duke research, and it has a name: sonoluminescence. A mantis shrimp punch is one of the few places in the natural world where you can find it happening on demand. So when the mantis shrimp hits a snail, the snail doesn't just take one impact. It takes two. The first is the physical club slamming into the shell at over 1,000 newtons of peak force, according to the Patek Nature paper. The second is the cavitation bubble collapsing right behind the club, sending another shockwave into the same spot a few microseconds later. The snail's armor cracks under a tiny biological double tap. And that double tap is exactly what makes the peacock mantis shrimp such a problem for aquariums. There are well-documented cases of these animals shattering the glass of their own tanks. Curators at public aquariums have to use thicker, laminated glass or acrylic specifically because the regular stuff cracks. A creature small enough to sit on a paperback book is breaking enclosures designed to hold tons of seawater. If you're enjoying this little guy as much as I am, hit subscribe. More stories like this on the channel every week. The other half of why this animal is wild is the part most people don't ever see because it lives behind those weird stalk eyes. The peacock mantis shrimp has one of the strangest visual systems ever found in an animal. Human eyes have 3 types of color photoreceptors. Most mammals have 2. Birds and many reptiles have 4. The peacock mantis shrimp has been reported to have between 12 and 16 distinct photoreceptor types, depending on the species, with some species sitting at the high end of that range. That is more than 4 times the channels your own eyes are running on. For a long time, biologists assumed this meant the mantis shrimp must be seeing colors that humans cannot imagine. A psychedelic supervision, basically. But the research complicated that picture. When mantis shrimp were trained to discriminate between different wavelengths, the animals were worse at telling subtle color differences apart than humans are. Which is strange, because you'd think more receptors would mean better discrimination. The current best guess is that the mantis shrimp's brain isn't comparing receptors the way ours does. Our brains take signals from 3 receptor types and run them through complex math to construct the colors we see. The mantis shrimp seems to skip the math. Each receptor channel fires its own signal, and the animal recognizes a color the way you might recognize a face. Fast, direct, without the heavy processing. It is a different strategy for seeing the world, optimized for speed on a coral reef where lunch and predators both move quickly. The eyes also pick up signals our eyes physically cannot. They see deep into the ultraviolet, which means the reef they live on is patterned in ways invisible to us. Even stranger, mantis shrimp eyes can detect circularly polarized light, which is a property of light involving the corkscrew direction its waves spin. No other animal on Earth has been confirmed to do this. Some species of mantis shrimp appear to flash circularly polarized signals on their bodies that only other mantis shrimp can read, which means they have their own private communication channel running on top of everything else. So you have an animal with the fastest mechanical strike in nature, a built-in cavitation shockwave, body armor that handles being smashed into things at small rifle speeds, and an alien visual system with a private color band reserved for its own kind. All of it packed into something the size of a small banana. And then there is the part where they remember you. Studies in invertebrate behavior have found that peacock mantis shrimp can recognize individual neighbors. They use chemical cues in the water and visual cues from those polarized signals to keep track of which mantis shrimp in the burrow next door has already lost a fight to them, so they don't waste energy fighting the same rival twice. They live in long-term burrows, sometimes for years, and they form what look like miniature truces with the neighbors they've already sorted out. The club itself has become its own field of study. Material scientists have been picking apart how a piece of exoskeleton can survive thousands of impacts at those acceleration numbers without shattering. The answer, according to research summarized in Integrative and Comparative Biology, is a layered architecture inside the club, with fibers wound around the impact surface in a corkscrew pattern that stops cracks from spreading. Engineers are now copying that structure to design tougher body armor and impact-resistant aerospace materials. The mantis shrimp has, in effect, been running a materials science lab inside its own arm for hundreds of millions of years, and humans are just now showing up to take notes. If you sit with it long enough, the truly weird thing is how easy it is to walk past a tank with one of these in it and miss what you're looking at. The peacock mantis shrimp looks like a brightly painted bug holding still in a hole. But behind that hole sits a creature carrying a saddle-shaped spring, a pair of cavitation cannons, 16 color channels, a private signaling system, and a memory long enough to track its neighbors by name. It is the entire toolkit of an over-engineered alien probe, scaled down to fit on a piece of coral. If you ever stand in front of a public aquarium and the keeper says, "Please don't tap the glass on this tank," the polite reason is stress on the animal. The honest reason is that the animal might tap back, and the glass is the part that loses. If you found this fun, there are more stories like this on the channel. See you in the next video.